Consider, please, a sealed container. This container has water in it, but you'll notice there's something else on the sides, and you've probably seen this before. You could call it condensation. Some people call it dew if it occurs naturally. Today, I think we're going to understand that, the idea that a liquid and a gas can exist in the same place and can change from form to form. So we're really getting into phase changes, and today we're talking about phase equilibrium. What I mean by phase equilibrium is I mean these two phases can coexist. So let's make our fluid purple. I'll make a gray container, and inside of our sealed glass container, or I guess it could be plastic, I'm going to put the purple fluid. And here it is, and there's a whole bunch of purple fluid down here. It's just solid purple fluid, and there's nothing up here. Up here we're going to have a vacuum. All right, so then if I wait a moment though, you see that purple fluid that's down here, that has a distribution of speeds. Remember Maxwell had told us that there's this distribution of speeds. If I say this is the probability of finding a certain atom at a certain speed or a certain molecule at a certain speed, there's an average speed, and there's this weird tail, and actually we can rank all three of these. We can say there are three different regimes of speed that you could have right here. You could say there's a most probable speed. What color do I want here? That's the peak of this graph right here. This is the most probable. And then there's this other speed that's slightly more than that, and I'll call that the average. That's this speed right here. That would be like add them all up and divide by the total number of possible speeds. But you see, because this is not a symmetric curve, the average is a little bit to the right of the most probable speed, because there's this wide tail over here on the right of probability. And then I guess there's one more interesting speed, and that would be this idea of a root mean squared speed. And we'll talk more about this. This is going to be VRMS. Maybe I should go into that right now. What I was thinking about VRMS, do you remember that we said, maybe it was 2 lectures ago, that the average kinetic energy is 3/2 kT for a monatomic ideal gas. And I want to define this thing that I'm calling, well, this is obviously 1/2 mv square, and then I'm going to be taking the average of that. I want to define this quantity that I call VRMS. It'll be the first time we see it, but not nearly the last. That's going to be V squared average screwed. That's why we call it root mean squared. We'll say that one more time. We call it root because there's a root, and we call it mean because that's an average, and we call it square because that's the square. It's the opposite order in which we're actually doing the operations, but it is the root of the mean of the square of v. So that's why it's root mean squared velocity. Now, I can tell you that if we take this quantity, we're going to say that the mass of a particle isn't really changing. So we could say that, oh man, can we do this? Can we say what V square average is? V square average, if I just solve this equation, is 3/2 times kT. We'll get back to phase equilibrium in just a little bit, but I'd forgotten to do this. It's very important. And then, oh man, we got this 1/2. So I get that 1/2 is going to cancel out this 1/2. So, well, let's see, I'll just multiply the whole thing by 2, and I'll divide the whole thing by mass. And then if I were to simplify this and also take my scroot so I could get to VRMS, I'm going to tell you that VRMS, well, VRMS is 3 kT. See that the 2's cancel? Let's explicitly cancel those 2. Okay, and then we're going to be dividing by the mass of each molecule and then scrooting. Fair enough. But the mass of a molecule is equal to the total mass of the system. This is a capital M divided by Avogadro's number. No, just kidding. No, it's the molar mass. Let's say this is the mass of a mole. That's a mass of a mole of the stuff, and then I'll divide by Avogadro's number right there. If I wanted to divide by the total number, not Avogadro's number, then I would get the mass of the system. But this is the mass of a mole, so I'm going to plug that in right now, and I'll say VRMS is, well, I'm plugging it in the denominator, so I'm going to get 3 times Avogadro's number times Boltzmann's constant, remember that's what K is, it's KB, times T divided by the molar mass, and I'll scroot that sucker right there. But the number, Avogadro's number times Boltzmann constant, well, that's just Ara. So I'm going to keep going over here to the left, and I'm going to get 3 times Ara, the ideal gas constant, times temperature divided by the molar mass of a substance. Chemists will probably be putting it in this form right here. Physicists will probably be putting it in this form right here. Chemists like to think about lots of things, and physicists like to think about the individual particles that are making it up. And there we are. So, back to the idea of phase equilibrium. If I've got a vacuum right there, and I've completely lost this page, so I will, what was I going to say? Oh yeah, there's this probability distribution. I was going to say that some of these molecules are going really, really fast. Like these guys over here, those guys over here are going fast. And those guys have enough kinetic energy to actually break free of the intermolecular forces right here. And they go, pew! And then pew, and they're free, whee, and they populate a gas up above. So let's see what happens after that. Carefully tear here and show you that we can draw another sealed. We can draw another sealed container and put the gas in there and see what's going on. There will come a time when all of the molecules with enough kinetic energy have in fact escaped. So the fluid level doesn't change much, but we've got these guys floating around up here. Okay, and I'm going to say that that is phase equilibrium. When the ones that have been going fast, wait a second, this equation over here for temperature, it says average kinetic energy is 3/2 kT. If the fastest molecules go out of the fluid, what happens to the average kinetic energy? If the fastest particles leave the fluid, the average kinetic energy will decrease. So guess what's decreasing? Boltzmann's constant, you think? No. 3/2, you think that's going to decrease? No. That's stupid, don't say that again. All right. Then the temperature has to decrease. Dang, the temperature decreases. Therefore, if the temperature decreases, that means that this is evaporation, and evaporation lowers the temperature, which is why you sweat. You could say, if you wanted to be fancy, you could say evaporation is endothermic. It is smart to sweat because sweating causes the highest energy particles on you to leave. And that means that the average kinetic energy of the fluid that's wrapped on your body because you've nasty been sweating all day, gross, is less. With less kinetic energy, you have a lower temperature, and that's why it's cool to sweat. Oh, we could put that'll be our slogan. It's cool to sweat. Maybe now you'll remember. Next, we need to go into this idea of equilibrium a little bit deeper. What if some demon came by and put a whole bunch, let's say we've got the same fluid right here. If some demon came by and put a whole bunch of gas up here, like too much, then you would find that, well, you know what gases are. It's randomly moving particles, and they'd be like, some of them land here on the fluid, and if they're not going quite fast enough to escape again, then there will be a net flow that direction if there's too much pressure. So I'm going to say too much pressure, and this is the pressure of the vapor, right? And this is too little pressure. Or another way to look at it, ooh, how could I get from having too much pressure back to an equilibrium? How could I make that too much pressure be an equilibrium? Well, if I had too much pressure and I wanted to get to equilibrium, I could just wait because they will, oh, let's put a verb on this. This is condensation. So this would be condensing. And this stuff right here, this is evaporating. Probably some really nice origin of that word, to become a vapor. You see the vapor right there? Okay, so you've got evaporation to get some vapor pressure increasing, and you've got condensing to make some condensation to make vapor pressure decrease. And what does temperature have to do with all of this? If I take a fluid and I heat this, if I heat this, then suddenly it's going to be, what, too little or too much? What is equilibrium vapor pressure? We're going to have to make a graph. We'll make a graph of the vapor pressure as depends on temperature. Would you believe that vapor pressure increases if the temperature increases? I think that makes sense. Because if I heat this, then there are more particles with larger kinetic energies. Temperature increases, average kinetic energy increases, and the tail there, the tail on this graph, I'm going to keep drawing this graph because it's so cool. This is probability versus speed. The tail here goes way out, and as the temperature goes up, this whole curve moves to the right a little bit. So we get more and more, a greater and greater fraction of molecules that have enough kinetic energy, enough speed to escape from the intermolecular forces forever to become a gas. Then, the final thing that I want to say about this is, here's a graph. We're going to get a really nice conclusion from this. This is vapor pressure of a gas. In this case, this is going to be water vapor because that's a nice concrete thing to deal with. This is temperature in degrees Celsius. And, well, let's make that graph. And it looks like this. It's this cool looking quadratic function. And if I check this out. I'm going to ask you what the vapor pressure is at 100 degrees Celsius. Do you have any idea what the vapor pressure of water is at 100 degrees Celsius? The interesting thing about it is that is atmospheric pressure. In fact, it defines atmospheric pressure because that's the temperature at which water boils. So we can write ourselves a little statement, and I'm going to say a liquid boils. Boils is a little bit harsher of a term than evaporating. Remember, the evaporation could happen way lower. You get a vapor pressure that's not zero whenever there's evaporation. So even down here, you've got vapor pressure of water. That's because, well, I guess that's because water evaporates. So water evaporates way earlier at a way lower pressure than it does water evaporates at a way lower temperature than it actually boils at. But a liquid boils whenever, let's put this in here, whenever the vapor pressure equals the external pressure. So, what would you do to make water boil at a lower temperature? Like 80 Celsius. What would you have to do to make water boil at a lower temperature? What would you have to do to make water boil at a higher temperature? What if you wanted to cook your potatoes, but the problem with potatoes is you want them to be in water, right? Because you want them to be moist and squishy. What if you wanted to cook your potatoes a lot faster, though? And you know that cooking potatoes at 100 Celsius is nice and slow. But what if you wanted to cook your potatoes really fast? You could get something called a pressure cooker, And that sucker would increase the pressure on the vapor on your potatoes. And the water then would not boil until it got much warmer. This is a larger pressure. If you put something in a pressure cooker, or even fancier, an autoclave, you can get liquid water at 120 Celsius. Sure, because the pressure's so dang high. And if you wanted to get water to boil at a much lower temperature, in fact, you wanted to reach the triple point of water, maybe you want to see water boil and freeze at the same temperature and pressure, then you decrease the pressure. I have a student who's working on that right now. One more thing. If you wanted to go back, where was that cool thing? Oh, I wrinkled it all up. That was dumb. If you wanted to go back and increase the bonding, if you go to this thing right here and you increase the bonding, would you be increasing the vapor pressure or decreasing the vapor pressure? If I have more bonding in the liquid, then I would encourage stuff that happened to hit it to stick to it, and I'd make it hard for things that were in it to escape. So I would decrease the vapor pressure. Let's see if I can write that down. I think I can. Vapor pressure down if bonding, intermolecular forces go up. And in one way to, if vapor pressure goes down, then if vapor pressure goes down, then would something be more likely to boil or less likely to boil? What do you think? Vapor pressure goes down, vapor pressure goes up, equilibrium vapor pressure. Yeah, I don't know. You think about that. Okay, I'll tell you. If vapor pressure goes down, bonding goes up to cause that. That would be like putting salt in water or something, and that makes it much stronger. Hydrogen bonds and intermolecular forces and blah, 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 blah. But the key is, if the bonding goes up, the vapor pressure goes down, then the boiling temperature goes up. So that's why putting salt in water causes the boiling temperature to go up, because the bonding has increased and it's not as inclined to boil because the vapor pressure has gone down. Bye-bye. Solid purple fluid. And there's nothing up here. Up here we're going to have a vacuum. All right, so then if I wait a moment though, you see that purple fluid that's down here, that has a distribution of speeds. Remember Maxwell had told us that there's this distribution of speeds. If I say this is the probability of finding a certain atom at a certain speed or a certain molecule at a certain speed, there's an average speed. All that V average, that's this speed right here, that would be like add them all up and divide by the total number of possible speeds. But you see, because this is not a symmetric curve, the average is a little bit to the right of the most probable speed, because there's this wide tail over here on the right of probability. And then I guess there's one more interesting speed, and that would be, consider please a sealed container. This container has water in it, but you'll notice there's something else on the sides, and you've probably seen this before. You could call it condensation. Some people call it dew if it occurs naturally. Today, I think we're going to understand that, the idea that a liquid and a gas can exist in the same place and can change from form to form. So we're really getting into phase changes, and there's this weird tail, and actually we can rank all three of these. We can say there are three different regimes of speed that you could have right here. You could say there's a most probable speed. What color do I want here? That's the peak of this graph right here. This is the most probable. And then there's this other speed that's slightly more than that, and today we're talking about phase equilibrium. What I mean by phase equilibrium is I mean these two phases can coexist. So let's make our fluid purple. I'll make a gray container, and inside of our sealed glass container, or I guess it could be plastic, I'm going to put the purple fluid. And here it is, and there's a whole bunch of purple fluid down here. It's just